Good morning, everyone. It's a great honor for me to receive this prize, and so I thank the organizers and the nominating committee for nominating me, and I also thank the department, Professor Zhao and Ling-Shu Zhu, for the work they put into getting me to come here, and to Tara Deo, who helped with the logistics. So I thank them too. Also want to thank the other people who've attended this conference, because I know a lot of them have come in support of me. So Weizor, sitting here, is one of my past students. Has come. Wolfithian has come. He's my also one of my past students, both very illustrious students. Martin Wainwright, I think he came because he wanted to be here, but he's a co-author of mine. We wrote a book together with Rob Tibshirani, so we're very happy to have him here. Zhejun Zhu is also one of my past students, also illustrious student. She's here, so thank you all for coming. And I'm leaving some people out, and well, that's what happens when you get old. Who did I leave? Yeah. Anyway, so this talk is on a project I did recently with Rob Tibshirani and Saurav Chatterjee, and the pictures that you're seeing here are the Sequoia Hall, which is the statistics department, has been for a long time. And then the picture on the right is the new data science building at Stanford. It's just opened, and it's a magnificent building. And part of our department has moved offices into that building. It's just over the road from Sequoia Hall. And so this is an exciting time for applied statistics data science at Stanford. So Professor Rao has been an important part of my whole statistical career. He's a legend. Of course, famous for these two landmark theorems, which appeared both in 1945 when he was in his 20s, which was rather remarkable. And they had a lot of staying power. So I grew up in South Africa, and C.R. Rao was a common name in statistics in South Africa. South Africa was a very multivariate statistics-centric environment, and so he was one of the names. And when I did my undergraduate degree at Rhodes University, I did they normally have a 3-year degree, and then you do 2 majors, and then if you do an extra year, it's called the honors year. So I did honors in statistics. And as part of the honors, my professor had me read 2 books. One was T.W. Anderson's book on multivariate statistics, and the other was Linear Statistical Inference and Its Applications by C.R. Rao. And these books are a little hard, both of them a little hard for an undergraduate student, you know, but I soldiered on, and I confess at the time I didn't understand a lot of it, but I tried hard. And it was honestly one of my inducements to carry on and study further and do a PhD. And this is actually a picture of my own book that's from my bookshelf. And then that thing sticking out the top is my bookmark. So some of you may recognize what that is. It's a, yeah, it's a punch card from a computer, yeah. So you don't see many of those around. And I had to hunt through, and this book actually had one in there. So there we go. Yeah, so it was an important part of my of my statistical training. Okay. These are my two immediate office neighbors at Stanford, Saurav Chatterjee and Rob Tibshirani. And Rob and I have written lots of stuff together, and we've got 5 books. And Saurav, I've never done anything with, nor Rob, but he's a theoretical powerhouse, and so we wanted some theoretical support in this work, and so we asked him, and sure enough, he delivered. And there's, thanks to a lot of other people, Rob has been talking to lots of people on this project, and some of them, many of them are, at least 2 of them are here. Okay, so I'm going to first tell you about well, we all know about the lasso, but just to remember what the lasso is. And here we do it for squared error loss. Solves the optimization problem, the lasso, and with a penalty designed to impose sparsity on the solution. So we got the sum of squares, and we got a bound L1 norm on the bound, a bound on the L1 norm of the coefficient vector, which we often write in the Lagrange form or penalty form, where we put a plus lambda times the penalty. So the penalty induces sparsity, and so that leads to feature selection. So this was a convex way of doing model regularization, reduce variance by shrinkage, but also induce sparsity. And being convex, it means it's good for computation. And because of that, there's a lot of software packages for fitting such models. The one we've provided in R is called GlimNet, and fits lasso and elastic net models. And there's been a bunch of contributors to this package. And recently, there's a new package called Adeli by my student James Yang, which is written in Python, for doing the same thing. And it actually works for it was intended for the group lasso, but includes the lasso. So a little bit of marketing. GlimNet, these are the cumulative downloads since GlimNet came out. And you can see the package, we've up to 8 million downloads. So it seems to be growing, although I think Python will start affecting this curve, because sadly, for me anyway, sadly, a lot of statisticians are moving across to Python. The daily package is getting a lot of interest from the community as well. Okay, so this is a motivating example. In biology and medicine, we've got 559 protein biomarkers measured on 81 patients. 20 are healthy and 61 have cancer. So it's a small data set, more variables, more features than observations. And in the top part of the display, we show the model chosen by lasso. And let's see. So these are the lasso coefficients. And we show in the univariate coefficients as well. So we fit this model by least squares. It's a binary outcome, but it doesn't matter. We just fit it by least squares. But these are the univariate least squares coefficients. And these are the ones delivered by lasso. And the one thing, the ones highlighted in blue, is that you've got two variables, 2 biomarkers, it's just numbered here, that have reasonably prominent multivariate coefficients, but they didn't show up at all really in the separate variable univariate least squares, right? So the model we're going to present does something a little different. We call it unilasso. So it's univariate guided lasso. It comes up with a different set of variables, and the variables don't overlap much. Both models were selected by cross-validation, and they both have about 95% accuracy. So they're both doing about as well. But by design, the unilasso coefficients all have fairly strong univariate support, right? And moreover, you'll notice they keep the same sign. Okay. Well, that's by design. Both of those are by design. And so we feel like we prefer this model than this one. And also, this is a much sparser model. It's got fewer variables in it. Okay, so, you can, if you go to your collaborator and defend a model and say, this is the model that we came up with, it's likely they're going to recognize the variables that you've provided, because the variables show univariate support, and so it's going to mean something more to them. Okay, so this is the outline of the talk. So the things we want to achieve, which I try to illustrate there, is we want to produce a model where the signs of the final coefficients agree with the signs of the univariate coefficients, or otherwise they're set to 0. Right? So there's this big caution there, because that's kind of stands up against what we teach in every time we teach multiple linear regression, right? We very quickly move to find examples where, when you fit things in a multivariate way, all stuff can change. There can be correlations in the variables, signs of variables can change in it, right? Well, we want to avoid that in the way we do our modeling. So I think the way to think of this is, when you think of the lasso and you put a penalty on sparsity, that penalty on sparsity, that's already put in some kind of prior belief that you don't need all these variables. You've got to, particularly if you've got a wide data set, you've got a lot of variables, you need to do some selection. And so you want to set the weaker variables, their coefficients, to 0, and just pick so you put in some kind of prior. So we're going to put some additional priors on, especially for wide data sets, that if there's a lot of different competing models that are somehow equivalent, we're going to pick the ones where the variables sort of agree with the marginal view, because it's going to be easier to interpret. Okay, but we put the caution there because it sort of flies in the face of common thinking for fitting linear models. And then also, features with larger univariate coefficients should be given a boost in the final model. Okay. So this is the idea of unilasso. You compute the univariate least squares coefficients, call them beta j hat, beta 0 j hat, for each of the p features. And then you fit the lasso with no standardization and non-negativity constraints to target y and the scaled features xij beta j hat. So you take those univariate coefficients and you multiply them by their feature, right? And that becomes your new feature. And that's what gets put in the second stage model here. And then you put a penalty, and then you multiply by thetas, and you put a penalty on the thetas. The thetas are all positive now, because you want the final coefficient, of course, is going to be the product of these two, and you want it to have the same sign as beta j hat, right? So theta j has got to be positive with that. And so this is the same as the absolute value, right? And notice, so apart from the positivity, notice that if you scale up features that have got strong univariate coefficients, the penalty treats it more gently, right? Because its coefficient doesn't have to be big for that variable to have an important effect. So it gives it a break, right? And then, so you solve this model, you select lambda by cross-validation, and then you compose the final model is given by this expression over here, and you know, and you combine the thetas and the betas. Right? So that's the uni-lasso idea. So you can actually interpret this idea exactly as a form of adaptive lasso, which was Hui Zhou's invention in 2006. The story is pretty much the same. You've got the univariate coefficients. Everything's the same. And now we directly fit a model for the gammas, right? The gammas were in the previous slide. There was the final coefficients, right? And so, yeah, we directly fit a model for the gammas. But now the univariate coefficients come into a penalty weight for the lasso penalty. So 1 over norm of beta j hat times gamma j, and there's a lambda here. And then the constraint becomes a sine of gamma j must be equal to the sine of beta j hat. So that's exactly equivalent to the previous slide. Right? And maybe this more evocative even, because it's saying you're giving a break to the variables that have got larger univariate coefficients. The penalty counts less. Right? So why do we do this way rather than this way? Well, because neither of them are good. And the problem is that, and the problem is easier to see in this form. Since we have used the data in step 1, we can get severe overfitting in step 2. Right? We've used the data, in particular y, to learn beta j hat over here. And now we're going to happily go ahead and fit the coefficients theta to this problem here. But now the y is already involved in beta j hat. And if we use cross-validation to select lambda, there's clearly some leakage of information. It's not going to actually work well, and it doesn't. It works terribly. So in this case, so even though these 3 slides have explained what we do, it's not actually what we do. So what we actually do is this. In the first step, instead of just computing the univariate coefficients, we compute the leave one out coefficients, or LU coefficients, right? So I think you all know what that means. When we fit the univariate coefficients, we get a coefficient for each observation, because for each observation, we leave that observation out and compute the coefficients on the rest. We do that. You can do that very efficiently in, you know, not much more than the cost of just an ordinary least squares fit, right? And then we got these leave one out coefficients. We get the leave one out fitted values, and then we put the theta j there. So this part is the same as before, and we solve this problem, this lasso problem. But now these are all leave one out. So this yi has not seen, is not involved in computing this derived feature here, right? And then we do cross-validation, the rest is the same. So that's what we do, okay? And so this step here looks a bit complicated, is so that we can avoid the overfitting problems, and that we found that we had before. You may wonder why over here we just have the beta j hat, and over here we have the intercept as well as the slope. Well, what happens with leave one out, actually, Wolf Fithian and I know a little bit about this. When you do leave one out, the intercept will jump around quite a lot, right? So things jump around, and it turns out that this is actually needed. You can't rely on a single intercept in the model to take care of all the intercepts. Okay, so that's the idea. I know it's a bit of a mouthful, but it's not really that complicated. So the use of the LU estimates to scale the features instead of the least squares estimates beta j is crucial to the success of the methods for the reasons that I said, because of overfitting. And also they create problems with selecting the lambda in step 2. We talked about the connections to the adaptive lasso, and the adaptive lasso uses any pilot estimate for beta, but we use the univariate least squares estimates. You can use this with any GLM, so I've just described it for least squares. In particular, all the methods covered by the GlimNet package, including the Cox model. And so we've created a unilasso package that implements this. There's a method in machine learning and statistics called stacked regression. And so this is for ensemble learning. You've got a bunch of different models fit to the data, and now you want to combine them together to get a sort of composite model. So what do you do? Well, you can take the fitted values from each of the models and then just combine them by a linear regression, right? But the stacked regression recognized that if you just did that, there'd be the same kind of leakage problems that we talked about. So what stacked regression recommended was doing leave one out fitted values for each of the models and then combine them by least squares. And so this is exactly a form of stacked regression, although I think stacked regression was intended for the case where these models here were much more complex models, but these were simple univariate models, but it is a form of stacked regression. Okay. So we got tons of examples, and I won't bore you with all of them, but Rob likes this home court example, which is home court meaning, you know, when you're playing basketball, which he loves doing. There's supposed to be a home court advantage, right? So the home court example is one that's supposed to work well for our method. And so you can see the construction is pretty much trying to mimic what we do in the model. You know, you boost up variables with strong univariate coefficients, and here we compare the mean squared error on test data of cross-validated lasso versus cross-validated unilasso, and it gets about half the mean squared error, and it gets smaller support. So what we really want here is small support, a good fitting model with small support, right? And so it achieves that. And in this case, we know which are the non-zero variables in the generating model. And sure enough, the true positive rate and false positive rate for unilasso does better than it does for lasso. So the home court example works, right? And then the counter, it's not hard to find counter examples for this method, because now we just go draw on our multivariable regression problems where coefficients change sign. And you can easily get an example where coefficients change sign. You create two variables that are very strongly positively correlated with each other. But in the true model, the one has a negative coefficient, the other has a positive coefficient, right? And if they're strongly correlated, they'll each have a marginal positive coefficient. But in the joint model, the one wants to have a negative. So that's going to fail. And sure enough, it does. I think that the thing is that a lot of the time, those examples are somewhat rare. And a lot of the times we think we're in that situation, but we've got fairly wide data and not too many observations. And just by chance, you're going to get things changing sign. So the point with unilasso is you can discover this, because if you find the fits are roughly the same, and this phenomenon is happening, you know, then it could be due to noise. And if you got the choice, you're probably going to pick the one where it doesn't happen. So this is an example. It seems that unilasso is more robust to adversarial attacks. So this is a machine learning and AI concept. You usually see it in the context of image recognition. You know, you've got an image of an ostrich, and you've got a classifier that's classifying animals or things or objects. And then you make a small bit of change to the image so that the human still sees an ostrich, but the machine learning algorithm says it's a vacuum cleaner or something. You know, so that's adversarial attacks. And so we used the simulation examples and put lasso and unilasso through some adversarial attacks, and unilasso does better than lasso. So it seems to be less susceptible. So a special case of unilasso is when you set lambda to 0. I nearly changed the slide and said, well, we should have the limit as lambda goes down to 0. But the positivity constraints are rather interesting. Even with wide data, when you fit a least squares model, just with positivity constraints on the coefficients. So if you've got n less than p, you tend to get very sparse models, right? So without doing anything, right? So, but anyway, that's what we call unireg. It's the same model as we had before, except we've got no lasso penalty because we've got the lasso penalty down at 0, but we've just got the positivity constraints. Okay. And so we still get sparsity because of this non-negativity. So here's an example. N is 300, P is 100, and 10% sparsity in the true model. And what you see here is the lasso path. We plot it as a function of log lambda. And what we're showing is the number of features selected by unilasso, which is green, and lasso, which is black, right? And so down at this end, this is when lambda is close to 0, so we're near the end of the path. And you can see lasso is selecting about 100 features, all 100, right? Which is what we expect, because that becomes least squares on 100 features. And unilasso is picking about 10 features, which happens to be about the right number in this case. And so the unireg is this guy over here, right at the end of that lasso part. Right? Okay, so we've got a bunch of simulation settings: low signal to noise ratio, medium, high, and home court example. And we report, so now N is 300, P is 100. And so we're just reporting the results of linear regression versus unireg. So this unireg is now thought of as a competitor to just linear regression, right, without any lasso. And we see that actually unireg does really well. Well, this is a bad situation for linear regression. 300, you got basically 3 observations per parameter, right? So it's slightly unfair, but unireg does much better throughout. And of course, it's got very good support. I mean, very small support. So it seems to work really nicely. Then we took all the 23 regression data sets on the UCI archive, and we look at, in the left plot, so each point, each circle here is a data set. And in the left plot, we're looking at the ratio of the mean squared for least squares relative to the mean squares for unireg. So above 1, unireg wins, below 1, least squares wins. You can see, for the most part, they're rather similar. There's two cases where unireg wins really well. And sparsity-wise, there's no competition, right? I mean, unireg always has much sparser models than least squares by design. And here's a diabetes data example. This is a data set that's been around for a while. 10 baseline variables: age, sex, body mass index, and average blood pressure, and 6 blood serum measurements. So the number of subjects is 442, and their diabetes patients, as well as a response of interest, which is a quantitative measure of disease progression after 1 year after baseline. And we see the least squares coefficients with the stars indicating the significant coefficients. These are all strongly significant. And interesting that unireg agrees on some of the significant coefficients. So with unireg, we don't immediately get a p-value, but we use a bootstrap to get a confidence interval, sort of like a posterior interval for the coefficients. And so the ones with stars are ones for which the posterior, this 95% interval, is away from 0. And we can see it picks up a different variable that wasn't found in the least squares. And it also ignores a variable sex in this case that was found by least squares. They don't give exactly the same answers. And of course, it's a sparser model as well than the least square solution. And then we did a lot of half samples. We did 200 half samples of the same data and refit just to get an idea of the relative performance. So you see that linear regression and unireg, lasso, and unilasso all did pretty much the same in terms of mean squared error. And the support of average support of unireg and was about 7, lasso 5.5, and unilasso 10. Surprising, that maybe flipped around. The thing that was of interest, though, is that in lasso and least squares on these half samples, there were a lot of sign flips of what was thought to be important variables. So you can see for age, there was 119 had negative coefficients and 81 had positive coefficients amongst the 200 half samples, and S2 and S3. And the minus and plus here is the coefficients in the full sample. And lasso had less sign flips, but still a lot of sign flips. But unilasso and unireg have hardly any sign flips because of the constraints on the coefficients. Okay, so we did talk about the relationship with adaptive lasso. It was adaptive lasso is more general, where you have some pilot estimate for beta j for each of the variables, and you can raise it to the power v. And in the original paper, it was any root n consistent estimate for beta. But here we use the univariate coefficients. and the other difference is the use of the we have this way of using the leave one out coefficients in our formulation, which I pointed out earlier. Doesn't really work when you use the adaptive lasso formulation. You really need to express the model in that kind of regression formulation to do that. Oh, this is sort of interesting. If you've got an orthogonal design, all these models you can fit trivially, right? It's just become some kind of threshold function on the coefficients. You can do them one at a time. But these threshold functions are interesting to look at. So these are the well-known threshold functions for the lasso, right? It's just a translation down towards zero, hit zero, you set it to zero. This is what it looks like for unilasso. You can figure out the threshold functions. And so if it's, if the coefficient's small, it shrinks heavily. But if the coefficient, so this is going to be the univariate coefficient, and this is what gets shrunk, how it gets shrunken. And if it's a tall big, then it gets shrunk less and gets closer to the unshrunk version, right? So just looking at this picture and this picture, it sort of shows you that what unilasso is doing is moving somewhere from lasso towards L0 selection, right? That's what this pattern's kind of indicating. And I put in there the MC plus penalty, which is a penalty designed to go somewhere between L0 and L1. And you can see it does something very similar. If the coefficient's small, it gets shrunken heavily towards zero, almost hard thresholding, and then it very quickly just reverts to the unshrunken version. And so unilasso is somehow in the same, doing something similar to that. And okay, so I mentioned there was some theory. The paper's got a nice report on this theory. I'm not going to give you a lot, but I'll just mention in one slide to summarize the results. So for lasso, we got the usual conditions for support recovery and mean squared consistency are that the non-support features are not too correlated with support features, right? So the idea is you got a true model, you got, which are the non-zero coefficients for the true model, and you've got a bunch of variables. You're going to be able to uncover this asymptotically if the non-support features are not too correlated with the support features. So they won't try and steal some of the signal. And so that's called the irrepresentability or mutual incoherence condition. And our colleague Martin Wainwright knows all about this. And we have some, sections in a chapter in our book on statistical learning with sparsity that covers this in some detail. For unilasso, this is the work that Shurov did with us. The univariate and multivariate population coefficients must have the same sign for each feature J in the true support. So that's a condition that's needed. That's sort of a hard condition. And there's a sufficient condition for that, is that for each pair JK in the true support, if the correlation for that pair is positive, then the population multiple regression coefficients should have the same sign. And similarly, if the correlation is negative, then they should have different signs. So not particularly easy. You can't really check these conditions, but those are the conditions needed for the correct support recovery. It's also got a mean squared error result for unireg versus least squares. So if the multivariate population coefficients beta j and the univariate coefficients beta j uni have the same sign for all j, then the squared error between the unireg and the true mean mu is less than the squared error between the least squares and mu by a known amount, we see, well, no, by an amount where C is greater, CQ, where C is greater than 0, and Q is the number of J with beta J equal to 0 and beta J uni not equal to 0. Okay, so there's this nice formula. So here we only use the sign of beta J uni, not its magnitude in the unirig, right? We're only using the sign. Okay. All right. So this result is based on yeah. Okay. So our beta our unirig estimate uses the leave one out estimation, and this result didn't involve the leave one out estimation. But anyway, this is the result that we have so far. Okay. So in summary, we've in P bigger than N and N bigger than P settings with correlated predictors, sparsity 10% in population coefficients of mixed signs. This is for our simulations. Lasso and uni-lasso show similar mean squared error, except in highest signal to noise ratio where lasso does considerably better. In all cases, uni-lasso delivers considerably sparser models. We can design a home court setting. This is a different one to the one I showed, where uni-lasso wins by a small margin. And in our simulations, we included adaptive lasso and match methods, and they do consistently worse. Match meaning we tune the competitors so that their support is the same as uni-lasso, and they do much worse. So this idea can be extended in other ways. So here's one way. We have a training data set T and also an external data set E from the same domain, say a disease. And we assume that E does not contain raw data, but only univariate scores. So this is common in genetics. In genetics, you may have a GWAS study, and all you don't get all the data, but you get the summary statistics for each of the SNPs, saying what the coefficient or the standardized coefficient. So you get that information, but they're univariate coefficients, right? So the idea is to use E in step 1 of uni-lasso for the univariate scores and not use loose scores at all, right? So it's a sort of obvious idea. If you've got some coefficient from a different study, right, that can give you a clue of which univariate features are important, you can use those in that kind of adaptive lasso formulation to influence the results. And so here we show via simulation how that plays out. And so the first two pictures the first two plots that's just lasso on the original data set T, and this is uni-lasso on the same data set T. And then we start adding in some of these univariate coefficients from E, right? And you see you get a boost. And then only adding in 100, the top 100, you get quite a boost. You add in the next 200, you get even more. And then it sort of stays flat, right? And I guess E was very wide. If you added them all in, oh no, this is uni-lasso on all. This is actually using all the data in the two data sets. So not just the univariate coefficients. But that's how, that's a way one can use this idea, say in GWAS and places where they don't publish all the data, but they do publish these marginal results. So by now we have a lot of collaborators at Stanford who are actually trying this out because we've given them software and they're using it, and seem to be some excitement about the use. We have a paper. It's on archive currently. We've got a package which is on my GitHub site, Unilasso, and there's a Python version. One of our students, Sophia Liu, and there's a site for that. So that's it. Thank you very much.